Thank you very much. Thank you to the organizers for organizing this conference. There are many people that didn't see for a long time, so it's nice to see you. So today we'll be talking about how to relate the theory of isometric actions on Hilbert spaces to ergodic theory. So it's not working. So let me explain the context. So I take H to be a real Hilbert space. So usually it will be separable in this talk. So separable real Hilbert space. And it's known that whenever we have an isometry of H, then it must be affine. It means that it must be a composition of an orthogonal operator and a translation of the Hilbert space. So we have a decomposition of the isometric group of H into a semi-direct product like this. And an isometric action of a group G. So here in my talk, I will only consider countable discrete groups. So an isometric action is just a group homomorphism from G to the isometric group of H. And because of what I said before, this action will always decompose into a linear part, this pi of G, which is an orthogonal operator, and the translation by a vector, which I call C of G. And because alpha is an action, pi must be an orthogonal representation. And the map C from G into H must satisfy this cocycle relation. So basically, an isometric action is just an orthogonal representation perturbed by such a map, which is called a one cocycle for the representation pi. Okay, so it depends on the representation pi. And so there are the non-interesting isometric actions. These are precisely the actions that have a fixed point. So saying that alpha has a fixed point is equivalent to saying that the cocycle C of G can be put into this following form. So this is what we call a co-boundary. So there is some vector psi, which will be the fixed point for alpha, such that the C of G can be written in this form. So basically, if we want to study interesting isometric actions, we need to find non-trivial cocycles, so cocycles which cannot be put into this form. Otherwise, just changing the origin of the Hilbert space, and you are just studying an orthogonal representation, a usual orthogonal representation. So we're interested in non-trivial cocycles. So why is this notion interesting? So first, it's a natural extension of representation theory. So you are just studying representation, but with an additional data, which is a cohomological data that you add. So it's quite natural, and it's also related to geometric group theory because many examples of groups acting on negatively curved spaces, such as trees or hyperbolic spaces, admit interesting affine isometric action on Hilbert space. So there are some geometric constructions like this. Also, this theory is related to the study of approximation properties for groups. So, for example, there is this notion of Kazhdan's property T, which can be characterized using affine isometric action on Hilbert spaces. So we have this characterization that a property T group is characterized by the fact that every isometric action of G on a Hilbert space has a fixed point. So these are precisely the class of groups that do not admit any interesting affine isometric action on a Hilbert space. They are all trivial. They are all equivalent to representations. So examples are SLNZ or for n greater than 3, or more generally high rank lattices, for example. So there is also another approximation property which is interesting, which is the High group property. And it's known that a countable group G has the High group property if and only if it admits an affine isometric action on a Hilbert space, which is proper, meaning that the cocycle goes to infinity when G goes to infinity. So examples are free groups and some rank 1 Lie groups like SU11 or SO11. Okay. And so this theory now is very well studied. It has many applications to geometric group theory, fixed point theorems, group cohomology, and everything else. So the goal of today's talk is to relate this theory to ergodic theory. So I will present a way to construct in a very canonical way, from any affine isometric action, to construct some measurable dynamical system, a non-singular action, which will be related to I will try to relate the ergodic properties of this dynamical system to the geometric properties of the action. Okay. And this will be done using the Gaussian functor. So I will recall this. So when you have a Euclidean space, so Rn, you have the so-called standard Gaussian probability measure. So this is the famous probability measure for statisticians, for example. So it's given by this formula. It has density with respect to the Lebesgue measure. And I make the following observation, which will be important. If you have a vector psi in Rn, then you can view it as a function from Rn to R. So it's a random variable. So you just take, for every element x of Rn, you take the inner product with psi. So this gives you a random variable with respect to this probability measure. And when you view it as a random variable, its distribution is, again, a Gaussian distribution, but which is not necessarily standard. It has a variance which is given by the norm of psi squared. So we have this formula. And the important fact here is that this map, which goes from Rn into the L2 space of Rn equipped with this probability measure, which sends psi to this function psi hat, this map is a linear isometry. Okay, so we embed our Euclidean space Rn as a subspace of this L2 space in a natural way, and realizing every vector psi as a Gaussian random variable. So this is specific to the finite dimensional case. And it's well known that you cannot define, for an infinite dimensional Hilbert space, you cannot define an analog of the Lebesgue measure, a translation invariant measure, and you cannot define a Gaussian measure on the Hilbert space itself, using the formula that I gave before for the density. So you cannot do that in the infinite dimensional case. But surprisingly, there is an analog of the Gaussian probability space, and which is given by the following theorem. So if H is a separable real Hilbert space, one can construct a standard probability space that I will denote by H hat, equip it with a probability measure mu, and some linear isometry which embeds H, the Hilbert space H, as a subspace of L2 of H hat mu, in a way which is isometric. So it's a linear isometry, it's an isometric embedding of H, and which satisfies the following two conditions. So first, psi hat is a Gaussian random variable for every psi in H. So this is the first and most important property, which gives the name to this Gaussian probability space. And the second condition is somehow which only ensures that the space H hat is not too big. We just want that this family of random variables generates the sigma algebra of this space, which I omit in this notation, so it's implicit here. So you can see that in the finite dimensional case, you can just take H hat to be equal to H itself, equipped with the standard Gaussian probability measure that I explained before. So this is somehow natural generalization to the infinite dimensional case, except that we no longer realize this mu on H itself. We can no longer do that, but on some more or bigger or more abstract standard probability space. And the fact that is really nice about this theorem is that it's not only an existence theorem, but it's also a uniqueness theorem. So this space is essentially unique. So you have this random process, a probability measure, and a family of random variables like this, which give you this embedding. And this random process is unique. So if you have another triple, another probability space, and another embedding like this, then there is a unique way to identify them with a unique measure-preserving isomorphism. Okay? So this is really unique. And I make the following observation is that the law of this random process is completely determined by the geometry of the Hilbert space. So when you have these two random variables and you study the covariance of these two random variables, it follows from the definition that it must be given by the inner product between the two vectors. In particular, if psi and eta are orthogonal, then the associated random variables will be independent. Okay? So this is important to understand. It transforms orthogonal vectors into independent random variables. Okay. So, yes?
When you say that C hat has a Gaussian distribution, you mean as a random, like hat of X?
So it means that when so psi hat is a random variable so it's defined from this probability space into R. When you push forward the measure, it's Gaussian as a measure on R, okay? Yes. Okay, so now a nice consequence of the uniqueness of this Gaussian process is that whenever you have now yes.
Can you repeat the question by Nicolas? The question in the comments.
Okay, sorry. So the question was, what does it mean that the xi hat is Gaussian? What do you mean by saying that xi hat is Gaussian? I mean that as a random variable, when you take its low, which is a probability measure on R, it is a Gaussian probability measure. Okay? When you push forward mu and get a measure on R, you get a Gaussian measure. Okay? So what I was saying is that because of the uniqueness, we have this many nice functorial properties. And the first one is that whenever you have a U, which is an orthogonal operator on H, then there exists a unique measure-preserving automorphism of this probability space that I denote by U hat, such that when I apply it to xi hat, I get U xi hat. Okay? And this map will be a homomorphism from the orthogonal group of H into this automorphism group. So this relation must remind you of this relation that I wrote here, which is valid in the finite dimensional case. So in the finite dimensional case, this is just the action of the orthogonal operator U on the Euclidean space itself. Okay? This generalizes to the infinite dimensional case. And the proof, again, is just the uniqueness of this Gaussian process. Because if you take this triple, it realizes the Gaussian process in a new way. But because of the uniqueness, there must be a map which sends this one to the previous one. Okay, so this is just a tautology. And so this observation was crucial in, so this construction of the Gaussian process, I don't know how to attribute it. I don't know who discovered it first. I mean, it was discovered by many people in different contexts, in physicists, probabilists. So, but I think the first time it was used in the ergodic theory was by Kohn and Weiss in the 80s. And so they used this observation to say the following thing. So now if you had an orthogonal representation of G onto a Hilbert space, then using this functor, you get a probability measure preserving action, which I will denote pi hat, of G on this Gaussian probability space. And this is what we call a Gaussian action. So this was first studied by Kohn and Weiss, and they used this construction to get many applications. Because basically when you have just a countable group, you have no way to produce like this some PMP action, except maybe the Bernoulli action. And so if you want to have like a rich class of probability measure preserving action, you have to use this kind of constructions, using the representation theory of the group. So I was mentioning the Bernoulli action. Actually, it's a particular case of this construction. So if you have now G, which is a countable group, and you take the presentation pi to be the regular representation on the small L2 of G, then there is an easy way to realize the Gaussian process. Just take as a probability space, take R equipped with a Gaussian probability measure, and take the infinite product indexed by the group G. So you get an infinite product probability space. And then the Gaussian action is simply the Bernoulli shift on this probability space. You're just shifting the coordinates. So when you start with a regular representation, the Gaussian action you get is a Bernoulli shift. And if you take other representation, you will get different actions with various properties, and this is very useful. So, of course, one question is how to relate ergodic properties of this action to properties of the original representation we started with. And so in this context, there are many nice characterizations giving you a dictionary between the two sides of this functor, and which gives you nice if and only if characterizations. For example, the most important one is the following one, which tells you when this action is ergodic. So it's easy to see in the finite dimensional case, it's never ergodic because the unit ball is always invariant. But in infinite dimensional case, we have this characterization. If you have a representation pi, then the Gaussian action pi hat will be ergodic if and only if the representation pi has no finite dimensional subrepresentations. So basically this finite dimensional phenomenon when you have the invariant unit ball is the only obstruction to this ergodicity. So somehow what happens in infinite dimensional case is that all the mass escapes to infinity and the unit ball will have measure 0. So when you take spaces with larger and larger dimension, the Gaussian measure of the unit ball tends to 0. At infinity, you don't see it at all. So that's why you cannot realize the Gaussian measure on the Hilbert space. And that's why you can get this kind of phenomenon of ergodicity. So what you have to think as Gaussian action usually as in the infinite dimensional case as being somehow chaotic and having good mixing properties. Like you can see this on the Bernoulli shift, okay? Okay, so now let me talk about, what I'll be talking now is joint work with two Japanese colleagues, Yuki Arano and Yusuke Isono. And our first observation was to understand what happens about translations. So we saw how orthogonal operators act on the Gaussian space, but what happens for translations? So actually, this was already understood by Cameron and Martin a long time ago in a slightly different context of abstract Wiener spaces. But so we formulate it in a different way in this context of Gaussian probability space. And it says the following thing. So if you take a vector v in H, there will exist a unique automorphism, but non-singular automorphism, which is not necessarily measure preserving. So it's a non-singular automorphism of this Gaussian probability space, such that it sends this psi hat to psi hat minus psi scalar product with v. So here you have to think of the finite dimensional case. When you take this random variable and you translate the vector eta, you just get the random variable you started with minus this constant here. And so somehow you have to think as this TV hat to be a generalization to the infinite dimensional case of the translations in the finite dimensional case. So this is a non-singular automorphism. It means that it preserves the class of the measure. And actually, we have the formula, this following formula for the Radon-Nikodym derivative. So when you take mu, you push it forward by this translation. You get a measure which I call mu v. And you have to think about it as some Gaussian probability measure, but centered not at the origin of the Hilbert space, but centered at another point v. And we have the following formula for the Radon-Nikodym derivatives, involving this random variable v hat. So this is the analog of the finite dimensional case. In the finite dimensional case, if you take a Gaussian measure which is centered at a vector v, which is not the origin, and you look at the Radon-Nikodym derivative, you can just take the quotients of the densities, the normalization factor goes away, and you are left with the following formula. And when you write it down, it just gives you this. It's the exponential of, here we have the norm of the vector v, and then we just have this inner product, v scalar eta, but this is precisely what I call v hat there. So this is really the same formula. And again, once you know the uniqueness of the Gaussian process, the proof is very easy. You can just define mu v like this, use this as a definition, and then check that this gives you a new Gaussian embedding satisfying the same condition that I gave you before, this formula. And so again, by the uniqueness, you can just, there must exist a unique map which takes mu to mu v and takes psi hat to this, okay? So it's really a consequence of the uniqueness. So this is just an observation, which is really very closely related to the Cameron-Martin theorem. It's basically reformulation, okay. So now, why is this interesting? So now if you have, so we saw that for any v, we can define a TV hat, which is an action of translation on this Gaussian probability space. And what is nice is that all these maps now fit together in a very nice group homomorphism. So I say that the isometry group of H decomposes semi-direct product. So every isometry can be written uniquely with U composed with a translation by V. And if you send this to TV hat composed with U hat, you get a group homomorphism. So we get an action of the isometry group of H on this Gaussian probability space, but no longer in a measure-preserving way, only in a non-singular way. We preserve the measure class, but not necessarily the measure. And we have an explicit formula for the Radon-Nikodym derivatives. And this means now that whenever you have a group G which acts by isometries on a Hilbert space H, then you can construct this non-singular Gaussian action. So we call it non-singular Gaussian actions, which I denote by alpha hat, and which gives you a non-singular action of G on this Gaussian probability space. And this is the main object of today that we want to study. We want to understand how alpha hat and its ergodic properties are related to alpha. So the first here fact, so the proof is is a very nice exercise, actually. It's not very difficult, but it's not completely obvious. So if alpha hat admits an invariant probability measure, which is in the measure class of mu, absolutely continuous with respect to mu, this can only happen if alpha has a fixed point. Okay? So if alpha has a fixed point, say v, then the measure mu v will be invariant by alpha. And basically, we're just looking at the usual PMP, probability measure preserving Gaussian actions. But whenever alpha has no fixed point, then you can show that there is no invariant probability measure at all. And this means that this non-singular Gaussian action is not conjugate to any PMP action. It's really different from what we were looking at before. So we are really looking, in that case, to a new class of actions. And so, of course, this can only work if G does not have property T. Otherwise, you always have a fixed point. So basically, with this functor, we obtain a very large class of non-singular actions for all groups without property T. Okay? And this was actually one of our main motivations, because we really lack tools to produce interesting non-singular actions for groups in general. And so this somehow gives you a good way to produce such actions, but only for non-property T groups. Okay. Now, so what about the ergodic properties? How can we relate them to the geometric properties of the action alpha? So as I said before, in the PMP case, when you have orthogonal representations, the Gaussian action pi hat will be ergodic if and only if pi has no finite dimensional subrepresentations. It's what we call also weakly mixing. So in that case, we have nice if and only if characterizations. But for non-singular Gaussian actions, this does not work anymore. We no longer have such nice characterizations. And actually, at the beginning of our project, really were stuck into studying this when we wanted to study these actions, because we didn't really understand well why this happens, why this is so difficult. And it actually becomes much easier to understand when you understand this phenomenon that I will explain now. So when you have an isometric action alpha on H, so we decompose it like this as a representation, a linear part and a cocycle, you can define new isometric actions just by putting a scalar in front of this cocycle. So we just scale the cocycle by the scalar t. And when you do this, you get a new isometric action, which in general will not be conjugate to the first one. So it has the same algebraic properties, the same geometric and representation theoretic properties, but we just scaled the cocycle. And what is surprising is that the ergodic properties of this alpha hat t, this is what we call, I will call it alpha to the t, this new action. The ergodic properties of the non-singular Gaussian action associated to this can be very different from the ergodic properties of alpha hat. And in fact, as I will explain now, there will be some phase transition phenomena. So when t is 0, we are just looking at the linear part. But when t is larger and larger, we are giving more and more importance to the translation part, and this will change the behavior of the action. And there will be some phase transition when t goes from 0 to infinity. There will be some critical scales that the properties will change. And somehow, this is the reason this happens in the infinite dimensional case is that, so you see alpha t is actually conjugate to alpha, but not by an orthogonal operator, by an homothétie. So if you take a homothétie of the Hilbert space, which scales by a factor t, and you conjugate alpha, you get alpha t. But the thing is that in the infinite dimensional case, you do not have actions of homothéties on the Gaussian probability space. These are no longer defined in the infinite dimensional case. So even though algebraically they conjugate, when you look at them at the Gaussian probability space, they are no longer conjugate. And that's why they can have this kind of very different behavior. Okay, so I want to give you an example, and which will be good to understand everything, a good example of this phase transition phenomenon, and the examples will come from geometry. So I will be looking at groups acting on trees, but actually the construction is general. So I start with a metric space, X, and I will assume that X is of negative type. So this means that the distance is conditionally of negative type, and actually I will use this definition, which is more interesting for us. It means that you can find an embedding of the metric space X into some Hilbert space H, which takes the distance between X and Y to the square of the norm between the two images of the points. Okay? So there are large classes of metric spaces admitting such, which have this property, that there exists some embedding like this into a Hilbert space. And typical examples are some negatively curved space, such as trees, or hyperbolic spaces, or Hadamard spaces, or things like that. So it's some kind of negative curvature assumption. And the important thing here is to understand that if you assume that the span of X is dense in H, then this embedding is unique. There is a unique way somehow to embed a metric space like this into a Hilbert space, but it's only unique up to affine isometries. So you have two embeddings like this, which spans densely the Hilbert space, and then there is a unique isometry which takes one to the other by taking one embedding to the other, okay? So it is essentially unique, and it's because, I mean, if you know all these norms, basically you also know all the inner products and you know the whole geometry of this embedding. So it's completely determined by this condition that I wrote above. And for example, you have one intuition about this is that if you take 3 points which are lined on the same line, the same geodesic, you have this relation between the distances. You have equality here. And so this tells you that these two vectors that I defined here will be orthogonal. So basically, this functor takes orthogonal straight lines into orthogonal vectors somehow. So anyway. But the conclusion of this is that whenever you have a group, you have this action of this isometric group, the isometric group of X, it will, because this embedding is unique up to affine isometry, we'll get a unique action of this isometric group onto H, this space H, which satisfies this relation. Okay? And so this is very useful to construct examples of isometric actions, because now whenever you have a group acting on this kind of metric spaces, you get automatically an isometric action on a Hilbert space by this factor that I explained here. Okay, so this is a very good way to produce isometric actions. Okay, so let me now state our main theorem, which gives a good description of this phase transition for a class of actions coming from groups acting on trees. Okay, so I take T to be a tree, and just for simplicity, we assume that it is of bounded degree, okay? And I take a group which is acting on it. So for this theorem, you can think of, for example, the free group acting on its Cayley tree. Okay, this is already very interesting example. The free group acting on its Cayley tree. So here, my assumption in general will be that gamma is discrete in the automorphism of the group in the automorphism group of the tree. This means that the group acts properly on the tree, or that the stabilizers are finite. The vertex stabilizers are finite. And I will assume that it is non-elementary, so that it is non-amenable if you want, or it does not fix a pair of points on the boundary. So this is really important to really have a non-trivial phase transition. Okay, so think of the free group acting on its Cayley tree. This works. Then what we say is that there exists some critical scale, TC, which is non-trivial, I mean it's positive and finite, such that when you look at the non-single, so you look at the action that I explained in the previous slide on the Hilbert space, and you look at this one parameter family by scaling the cocycle T, by T. So when you look at the non-singular Gaussian actions associated to this group, they will all be ergodic for T less than Tc. They will be ergodic, and moreover, they will be of type 3. So what type 3 means is that there is no invariant probability measure, but this we already saw, this follows from the absence of a fixed point. But also it means that there is no invariant infinite measure also. So there is no invariant sigma finite measure. This is what it means to be a type 3. Type 3.1 is more subtle, but if you don't know, it's not very important. So what I'm saying is that it is ergodic and it has no invariant finite or infinite measure. And moreover, when you change the value of T from 0 to Tc, you get pairwise non-conjugate actions. So really get a family of actions that are different. But now, if you go beyond Tc, so if T is strictly larger than Tc, what you get is a completely different type of actions. So these are called type 1 actions. And it's actions which have a fundamental domain, okay? fundamental domain, you have a measurable subset of positive measure, such that the translates by the group are pairwise disjoint, and they cover the whole space. Okay, so you can pave the space if you want by this fundamental domain. Okay, so one remark about this kind of actions is that first they are never ergodic, because if you take the fundamental domain, you cut it into two pieces, and you translate one piece by the group, you will get a non-trivial invariant subset of your action. So the action is never ergodic. It has a lot of invariant subsets. And also it has many invariant sigma finite measure, because whenever you take your fundamental domain and you take some probability measure on this fundamental domain, and you translate this probability measure, you get an invariant sigma finite measure. Okay? So it's completely different from the first situation where it was ergodic and of type 3. Now it is not ergodic and it has invariant sigma finite measures. And what's interesting also is to notice that when you have action like this, which has a fundamental domain, they're all conjugate. I mean, there is only one action on a diffuse probability space which has a fundamental domain. It's basically just gamma acting on itself, but you take the product with some diffuse probability space, okay? So they are all conjugate. So really completely different type of behavior between these two phases, okay? We have a chaotic phase, which is the most interesting one, and a more ordered phase, which is the type 1 phase, where you have a fundamental domain. And moreover, we give a precise computation of this value of TC. And it's interesting because it's related to a well-known invariant for groups acting on trees, which is called the Poincaré exponent. So we have the following formula. So TC is given by this formula, 2 times the square root of 2 times delta of gamma. And what is delta of gamma? So this is it's a quantitative invariant for groups acting on trees, or on hyperbolic spaces also. And it's the absence of convergence of this so-called Poincaré series. So you are taking a sum over you fix some point x0 in your tree, and you look at this sum over the orbit of this point. And you look at how this, so here you're looking at the distance. This series will always converge for S large enough, and it will diverge for S small enough. And so the precise S for which it starts to converge, and this will be the Poincaré exponent. So intuitively, another way to define it is to look at the growth, the volume growth of the orbits of the action. So you take balls of radius r, and you look at the number of points of the orbit of x0 which are in this ball of radius r. So you count how many you have, you take the logarithm, and you look at how the behavior of this when you divide by r. It must converge to a constant which is precisely the Poincaré exponent. So somehow this Poincaré exponent measures the exponential volume growth of the orbits of the action, okay? Okay, so what I want to do, I have still some time to explain this. I want to explain why this phase transition phenomenon happens, and to give you some intuition about this.
Excuse me?
Yes?
What happens at t equals PC?
At t equals tc, in general, we don't know. It's very hard to understand what happens at t equal to tc. But, well, precisely for the free group acting on scaly tree, in that case, we can do the computation, and we know that t will be in the second case of a type 1 case. It will have a fundamental domain. Yes? Yes? Yes. Are the spaces associated with t in the first phase, between 0 and tc, all conjugated? The spaces. So the spaces are probability spaces, so they are all isomorphic. But the actions will not be conjugate. I mean, the space is fixed. It's always this Gaussian probability space. But I'm just changing the action. So the actions are not conjugated for t less than tc. And at t equal tc, as I said, in general, we don't know. So except for the free group acting with scaly tree, where we can do where we can determine this precisely. Yes.
I think you meant for t larger than tc.
Larger than tc? For t larger than tc, they are all conjugate, because they all have a fundamental domain. And for t less than tc, they are not conjugate. Okay, so let me explain. I mean, the key property to understand this phase transition is to understand the property called recurrence of the action. So how much time do I have left? We stop at 7 minutes, okay. So I would say that the non-singular action is recurrent if it goes, if whenever I take a set of positive measure A, then I will come back to this set infinitely many times, okay? I will come back to this set infinitely many times. So this is a property that was first introduced by Poincaré, I think. He proved that whenever you have a probability measure preserving action, it will always be recurrent, okay? A probability measure preserving action is always recurrent. It's somehow quite surprising the first time you see it. And, but for non-singular action, typically this does not need to happen. For example, if you have a fundamental domain, it will not be recurrent, because precisely if you take the fundamental domain and you take the translates, it will never come back, so by definition. So there is actually a nice criterion to determine when an action, a non-singular action, is recurrent. And basically, you can deduce it from the proof of Poincaré. When Poincaré proves that any PMP action is recurrent, actually, if you generalize a little bit, you get a criterion. And the criterion is the following one. So you take your measure mu, which is non-singular with respect to this action, and the action will be recurrent if and only if, when you look at this series, when you take all the Radon-Nikodym derivative and you sum over G, if and only if this series diverges almost surely. So for almost every point, this series diverges, because it somehow measures the expectations of numbers of returns into a set of positive measures. So this is basically the proof. Okay. So we have this criterion, and the converse, you can ask what happens if this series converges almost surely. Well, this precisely characterizes the case where you have a fundamental domain. So if the series converges almost surely, then you will have a fundamental domain. And this is what also we call a dissipative action. And in general, there will be some part of X on which it will converge and a part on which it will diverge. And the action will always decompose into a recurrent part and a part which has a fundamental domain. Okay? So we have this nice quantitative criterion. But now this is interesting for us, because now if you look at what happens for our non-singular Gaussian actions, so we have an explicit formula for the Radon-Nikodym derivative. And so when you want to understand when this action is recurrent, you have to take the sum over this Radon-Nikodym derivatives. Remember that when I act, the linear part does not change the measure, but I translate by C of G. So I change the measure, and I gave you before the Radon-Nikodym derivative formula, and it's given like this. It's given by this formula. So basically, the recurrence of the action is measured by the divergence or convergence of this infinite random series. Okay, so it's a series of random variables. And so now we made this proof with some brutal estimates, which gives you an estimate of when this series diverges or converges. And so basically, so you see this is now closely related to the Poincaré exponent, because in the case of groups, the norm of CG squared is basically the distance, is exactly the distance between x0 and gx0. So this is really a generalization of the Poincaré series for affine isometric actions. So this series, which coincides precisely with the Poincaré series in the group acting for the groups acting on trees, this series you see it's closely related to this one. If you omit the random part, if you remove this random part, C of G hat, you basically get the same series, except that you have placed S by T squared over 2. And so it's not surprising that this T is related precisely to the square root of 2 delta. Right? Or in other words, delta is related to T, the critical T squared over 2. Okay, so it's not surprising that this is related to this one. But in general, this random term, this oscillation term, will be important for the estimates, and we can change the value of this. So we do not have equality in general, and T-rec in general will only be bounded by these two extreme cases. So if you want to understand the precise value of this, you cannot only look at this series, you cannot only look at the growth of this cocycle, but you have also to understand the correlations between these random variables. Or in other words, the inner products between CG and CH for different G and H. So we have to understand this, and this makes it very difficult to compute in general. So basically, this upper bound comes when all these CGs behave as if they are independent, orthogonal, and this arises when they are all very much correlated. And between the two, it can be very subtle. So actually, with the only case where we were able to make the computations and show that this critical value will precisely be this is in the case of trees. As I explained, we have equality in this case, okay? And for this, we used like some really nice theorems about random walks indexed by trees. So we used like some probability theory to prove this. Okay, so I have maybe 1 or 2 more minutes. So as explained, this now criterion that I explained before allows us to understand when the action is recurrent. And this is actually precisely the key property that determines this phase transition. Once we understand when the action is recurrent, now we can try to understand when it is ergodic, what happens about these invariant measures and things like this. And for this, we have now nice criterions. So the first one is a criterion about ergodicity. So when you have an isometric action of a group G, and you know that its linear part, which is alpha 0, I mean its linear part, is mixing. So not only a weakly mixing is not enough, you have to assume that it is mixing. So this means that this pi of G converges weakly to 0 whenever G goes to infinity. If the linear part is mixing, then the action alpha t will be ergodic for all t strictly less than the recurrence scale. So in the first phase, the recurrent phase, the action will always be ergodic. So this is a very simple or general criterion. For determining the type, finding if there are invariant infinite measures or not, this is more difficult. So in our first paper with Arano and Isono, we didn't have a very nice general criterion. But for the case of trees, we were able to do it using geometric arguments about these actions. But later, with another work with Stefan Vass, we were able to give a very nice criterion, which basically allows us to understand, in general, for any isometric action, when you have a sigma finite measure or not. So we say the following thing: whenever you have an action which does not have a fixed point, so there is no invariant probability measure, there always exists some TC, which might be 0 or infinity, such that we have a first phase where the action is of type 3. And actually, it can be only type 3.1 or type 3.0, for those who know what it means. And we have a second phase for t larger than Tc, such that alpha t admits a sigma finite invariant measure, which is equivalent to mu, okay? So in general, this Tc is not related to the recurrence scale. There is some subtle phenomenon that can happen in general. But if the action is proper, and this will be the case for groups acting on trees, we know that this Tc is precisely the recurrence scale that I explained before. So when you have a proper action, we know that in the recurrent phase, we have no invariant measure. And in the dissipative phase, we, of course, have an invariant measure, as I explained before, because we have this fundamental domain. But in general, something more subtle can happen. So we give a more precise, actually, theorem which tells you precisely when can this phenomenon happen in the non-proper case. So we have a more precise statement. And so, okay, maybe I should stop here. So, okay, maybe I should stop. I don't know. Okay, thank you.
Okay, yes, Cyril has a question.
Yes. Okay, so given an affine action alpha of group G on a Hilbert space with cocycle C, the function, yes, is condition. There's a function which is the square norm of the cocycle is conditionally of negative type. By Schoenberg theorem, the function exponential of minus t psi is of positive type for all t from 0 to infinity. And we have the associated GNS representation, pi of t. Does the Gaussian action associated with pi of t coincide with our hat alpha of t? So no, so there is a relation, but this is not, I mean, if you look at the Gaussian action associated to this GNS representation, it will be PMP action, right? Because we have a representation, so it gives you a PMP Gaussian action. So it's different from what I'm considering here, which is non-singular Gaussian action, which is not PMP. However, if you take this non-singular Gaussian action and you look at its Koopman representation, which is a unitary representation, it will be not equal in general, but it will contain this GNS representation, okay? So if you just take the positive definite function coming from, so you have the Koopman representation, and you take the state coming from the vector 1 in the L2 space of this Gaussian probability space, you get a positive definite function, and it will be precisely the function you were talking about in this coming from this Schoenberg theorem. So,
Cyril?
There's two quick questions.
yes.
The first one is
Cheers. So 2 quick questions. The first one is it's related to your theorem with Stefan. So
Yes.
Below this TC, so it's type 3, but it may not be ergodic, right?
Yes, so I was not precise. So it might not be ergodic. So this is also surprising because here we can determine the type without knowing anything about ergodicity. So in general, it will not be ergodic. And what I said is that if it is ergodic, then it can only be type 3.1 or type 3.0. But in general, if it is not ergodic, it's more complicated. Okay.
Yeah, sure. And so regarding the sharpest result for groups acting on trees, if I
Yes.
remember correctly,
Mm-hmm.
so you said that below this critical exponent, then the actions are not pairwise conjugate.
Yes. Yes.
So my next question is, so is there some hope to prove that they are not pairwise OE, orbit equivalent?
Yes, it's a very nice question, but we don't know. Maybe there is some way to distinguish them up to orbit equivalence, but it's probably harder. Actually, the way we distinguish them, so I didn't have time to explain this, but it's using the rotation trick, and it's really a trick. It's not very, very deep. If you want to understand the orbit equivalence of these actions, you have to work. More. So,
Sure.
but yeah, it's an interesting question.
Thanks.
Yes. Okay. So does the Koopman weakly contain the original affine action as usual? So what do you mean by the Koopman? I don't know what it means that the Koopman contains an affine action. So, I mean, yeah, I don't know what you mean by weak containment for affine actions, but. Are there results for asymmetric action on Hilbert space which have almost fixed points? Yes, so this is an interesting question. There is a second question, which says what happens when you have almost fixed points for your action. So this means that you have your action will have an invariant mean. It does not have an invariant probability measure, but you have an invariant state, which is not normal, so you have an invariant mean. And so in general, so for example, it tells you that the action can never be dissipative. So this series will always diverge, for example. But it's not so easy to use to determine ergodic properties or type properties. However, there is a stronger notion of having almost fixed points, which we called evanescent. And so, okay, maybe it's a bit technical, but there is a slightly stronger notion that we can exploit, and we use this to prove many ergodicity results and type results about this action. Yes?
So you said that for the tree case, you are using quite specific geometry and also probabilistic tools.
Yes, yes.
So what kind of arguments are you using to treat the general case with in your result with
Yes.
VAS?
You mean this result with it's here where we use the geometric and the probabilistic argument.
Yes,
So
the other one, what do you use?
Yes.
The one with VAS.
The one with VAS, we do not use, we use, so there is a very technical part, but there is also, we use, this rotation trick part. So this is something I didn't explain, but I didn't have time to explain, but quickly, if you have a rotation, you look at H plus H, okay? You double the Hilbert space, and you look at this rotation matrix. So this rotation matrix will commute with pi tensor pi, pi plus pi, the linear part, but it will not commute with the affine actions. And what happens actually, it will conjugate, if you look at alpha on the left, first copy, and the linear part on the second copy, it will conjugate it to the sum of these two isometric actions, one scaled with t and the other scaled with s. And so this gives you an interesting relation between this. somehow, as I said, these actions are not conjugate because we don't have homothésis on the Gaussian probability space, but using this trick, we still have this kind of relation. We know that this is conjugate to this. So this is really the key tool we use all the time to relate this different action for different values of t and to understand the ergodicity. And what we did with VAS is to generalize this. So one ingredient of the proof is to generalize this to the Maharam extensions. So it's more subtle, and we have to change here the... So I can explain this later, but for those who know what Maharam extension is, you just put here Maharam extension everywhere, and here you have to change the action to twist it by its own cocycle. But anyway, so we have this kind of algebraic properties, and we exploit them with more functional analysis part. Anyway, so it's really more direct.
Okay, thank you. So let's thank